My name is Anna Steffi, and I'm part of Group 19.
My name is Zach Barnett. I'm part of Group 19.
I'm Alana Jadwalis, also Group 19.
I'm Jordan Chang, Group 19.
And this is going to be our recitation 11 video. And we can work on this. Okay. First problem talks about somebody catching a baseball being thrown to them with a mitt. They're wearing ice skates and they're on an ice rink. And it talks about what about the collision makes it so that we can evaluate parts about it. Then we have to find whether or not it's elastic or inelastic, and then our general formula for our final speed of this system. So did anyone want to touch on the first part of it?
Basically, I interpreted it as asking is like, why can we analyze this problem as specifically a collision problem? And I would just kind of went back to the definition of what a collision is, and it's talking about two bodies of mass interacting with each other and exerting force on each other. And that's pretty much exactly what this situation is. So that's my reasoning as to why.
And there's no like large external forces. It's all in the system.
Yeah, I think that's what I was thinking about too. It just sounds like a collision. And because it's been set up so that like she's on ice and all these other things, we only have like, we can set it up with the energy principle that we've been given so that we only have like one unknown, given a lot of data. For final speed, MV over the mass of the system is something we all got. And I don't think anyone has any questions there. And does everyone agree it's inelastic?
Yeah, sure.
Yeah.
Awesome. 6 together. And then part 2, it gives us numbers to calculate this. And because we all have the same numbers and we all have the same equation, all of our answers are the same. And when we want to talk about the thermal energy, I think we all got really similar answers to, I got 96.958, which is just a rounded value. And yep, these all look really similar. Did anyone get anything different for these? All right. And then for the next question, problem 2, part 1, we have the hydrogen atom, which is at ground state, and its first excited state is 10.2 electron volts. It gives us the note that the mass of a proton is much larger than the mass of an electron. And at first, we have to estimate the kinetic energy after such an inelastic collision and justify an approximation you use to make your estimate. And I think both of everybody, is this the same thing? Yeah. So this is just off of delta K being final and initial, the values you were given, that transfer of kinetic energy. And I think everybody had the same general idea. At this part, did anyone disagree with what we have? Awesome. And then now consider the collision of a proton with the initial kinetic energy. With a neutral hydrogen atom initially at rest, what levels of the hydrogen atom can be excited to? And I think that the mass of a proton is basically the mass of hydrogen atom. And then this is the initial kinetic energy. We can express this in terms of momentum conserved, which is really important because that means that the magnitude of initial, like our proton, will be the magnitude then if we had all of it. And then we can put this in terms of system. And then the system at the end is just the masses, because the masses are the same, which is very different than our initial, where one was much more massive than the other. And that makes 2m. And when you solve that out, the initial kinetic energy would be 1/2. And then 1/2 of the initial kinetic energy, which we found, was 20 electron volts, which is 10 electron volts. And 10 electron volts is very distinctly not 10.2. So the hydrogen atom fails to move to its final excited state. And I'm pretty sure we talked about that. Does anyone disagree, or is everyone okay with that?
Oh, I'm good with that.
I'm agree with that.
That's good.
And then, so the last problem, we've seen this a lot in, I think, either notes or homework or something, because I've seen this so many times. So it's a block being stretched to these 3 different lengths. Their resistance is negligible. How long does it take for the block to return to where it was released? And yeah, this is 2 pi over m over k. I think, did anyone get anything different?
Yeah, no, not different, but I just plugged the values in they gave us. So it's the same exact answer, just with values in terms of k.
Yeah. Yeah. Comes from there. Just comes, yeah, that honestly just came from my notes. Next, the block is again positioned at rest, and then we shoot a bullet into it. And the final speed of the block. How did we approach this problem?
Personally, I approach it pretty much like exactly the same as I did part 1, problem 1, with just looking at the momentum and realizing that it's going to be conserved, and seeing that the momentum of the bullet is going to equal the momentum of the whole system together, and just setting that equal to each other, and then solving for the final velocity. Yeah.
Yeah, that seems really good. I think, yeah, it's very similar in elastic collision. So 2 is now write an equation that could be used to determine how high the block goes after being hit with the bullet. And I think we had come to a consensus for Zachary's answer.
Yeah. So I had energy initial is equal to energy final, and then kind of broke that down further into kinetic energy and spring potential energy as being the initial energy, and setting that equal to the energy final of what I thought would be the potential gravitational energy of the whole system with both masses together.
Mhm.
And then solving just for height from that.
Yeah. I think, Alana, Gia, do you agree with this?
Yeah.
Awesome. And that is our last question, which was the height. Awesome. Does anyone have any questions before we end this call?
No.
All right.